right, so the last quantity that we have to generalize in this chapter, or these convert to angular sense, is momentum. So that's what we call angular momentum. So let's first talk about angular momentum. So what is angular momentum by definition? So let's look at a coordinate system. So let's say this is our x, y, and z directions. Let's say we have some particle of mass m, say set it here, moving in this direction with a velocity of v. So that its momentum then points in the same direction as the velocity. So this is my momentum vector. Well, from here we're going to define, again, a position vector r, which points from the origin to the location of the object. So this is r. We can then define what's known as the angular momentum, we call that L, as then being equal to r cross p. So this is my angular momentum, or this is the same thing as the mass times the radius crossed by the velocity. So again, r is the vector which points from the origin to the location of the particle, and then p is the momentum, or the linear momentum of the particle at that particular position. So, now, first of all, note that again, this thing is defined in terms of cross product. So if I wrote the magnitude of the angular momentum, this would then be equal to the magnitude of the r vector times the magnitude of the momentum times sine of the angle between the two. So, okay, so if this is my r vector, this is my momentum vector, then the angle between the two is that specifically that angle between those two vectors. And again, the direction of the angular momentum would be given by the right-hand rule. So in this case, we would point our fingers in the direction of the position vector, cross it then towards the momentum. So in this case, I point my fingers in the direction of r, curl towards p. So in this case, my angular momentum would be into the board. So this would be my L. Or again here, r is this way, p is this way, so L would then be, again, into the board. Now again, if I did that in opposite order, did p cross r, my angular momentum would still have the same magnitude, but in the opposite direction. Now, angular momentum is kind of a weird quantity. Now, what I mean by weird quantity is that means that even though an object can be moving in a straight line, it can still have an angular momentum. And the reason for that is, again, each person that is watching this, just like what we talked about position vectors as opposed to displacement vectors, each one is going to create their own coordinate system where they're going to be the origin of that coordinate system. So, for example, if you're sitting here and I'm moving in this direction, according to you, I have an angular momentum because I am moving. You have an r vector which goes from you to me. But not only that, but my angular momentum is changing with time, because even though if my velocity stays fixed, i.e. my momentum stays fixed, the direction of that angle between the two of us and the length of that vector r is going to be increasing, and that angle is going to be changing all the time. Which means, according to you, I actually have an angular momentum. According to me, I do not. Because according to me, as I'm moving in this direction, my natural coordinate system is this way, so I'm moving in a direction where r is equal to 0, because my momentum's in exactly 0 distance away from my origin, since my origin is always moving, which means I only have linear momentum according to myself, but according to you, I have angular momentum. So even though an object can have specifically linear momentum according to itself, but according to a different observer, it can have an angular momentum due to the fact that r and p are not collinear, meaning they're not in the same direction or in opposite directions for each other. So in that case, they would have an angular momentum. But angular momentum is, in most cases, just the momentum that this is carrying in an angular type sense, right? In a rotation type sense. So this is how we define angular momentum. Now, note that the time rate of change of angular momentum, so let's look at the time rate of change of angular momentum. So if I take the time rate of change of this is going to be the same thing as the time rate of change of the mass times r cross v. Let's do it this way. So this is going to be the same thing as the mass times, now this is a product of two functions, because this depends on time and this also depends on time. So this is going to be dr dt cross v plus r crossed by dv dt. But dr dt by definition is the velocity, so this is the velocity crossed by the velocity. But remember we said a cross product is how perpendicular two vectors are to each other. So is the velocity perpendicular to the velocity? Well, no, it's the same thing, so they have to be in the same direction. So the angle between these two things is 0, meaning they're actually parallel to each other. So this term has to be equal to 0. So it's going to be the same thing then as n times r cross dv dt, which is the same thing then as r cross dp dt. But from Newton's second law, we know that dv dt is the same thing as the force. So it's the same thing as r cross f. But based off what we just talked about, r cross f is the same thing as the torque. So what this says then is that what? The time rate of change of the angular momentum is equal to the torque on an object. Now, what happens if I have a collection of objects? Now I want to know, what is the angular momentum of that collection of objects? So let's say I have a whole bunch of masses. So M1, M2, M3, M4, according to some coordinate system. So this is X, Y, and Z. Well, again, each one of these guys is going to have their own radial vector. So here's going to be my R1, here's going to be my R2, R3, R4. Each one of them has their own momentum. So this one might be moving, I don't know, in this direction. So this would be P1, this would be, say, P2, this might be P3, this would then be P4, for example. So they all have their own angular momentum. So we're going to define then the total angular momentum. Let's call that capital L, is then equal to the sum, or the vector sum, of all of the individual momentum. So this is going to be the same thing then as the sum over I of Mi Ri crossed by di. So that the magnitude of this total angular momentum then is going to be equal to the sum over I of Mi Ri di sine of theta I, where theta I is the angle between all of the different r vectors and the angular momentum vectors. So in this case, this would be, say, theta 4, this would be theta 2, theta 1, and etc. So the total angular momentum then is simply the vector sum of all of the individual angular momentum. Now, what's the time rate of change of the total angular momentum? So if I look at the time rate of change of the total angular momentum, well, this is now just equal to the sum over the time rate of change of all the individual angular momenta. But we know the time rate of change of any individual angular momentum is simply the torques. So this is then equal to the sum over all the individual torques, which is then equal to simply the net torque. Now, what happens if the net torque is equal to 0? Well, if the net torque is equal to 0, what that means then is the time rate of change of the total angular momentum is equal to 0, which means that the change of angular momentum must be equal to 0, which means that the angular momentum must be simply equal to a constant. So, in this case, if the net torque is equal to 0, this tells me that my change in angular momentum must be equal to 0, which means that the initial angular momentum must be equal to the final angular momentum. This is what we call conservation of angular momentum. We'll talk about some examples of that in just a second. Now, the other thing that's kind of interesting is the total angular momentum of a rigid body. So here, this was a collection of point particles. Well, let's say I have a rigid body, which is actually rotating. So, for example, this ruler. And I want to know what is the angular momentum of this ruler as it moves through a circle. So let's draw our XY coordinate system, and let's say here is my object. Well, the total angular momentum of this system is then simply going to be, well, we're going to do the same thing we did before with center of mass. We're going to take this thing and chop it up into a whole bunch of small pieces. So let's say this is delta M1, this is delta M2, delta M3, and etc. So that this has a radial vector from the pivot point, R1. This has a radial vector from the pivot point, R2. This has a radial vector from the pivot point, R3. So that, again, the total angular momentum will then simply be equal to, so let's look at the magnitude of this, equal to then the sum over I of MI RI times VI times sine of the angle between the two. Now, if this thing is rotating with an angular velocity of omega, what has to be true then is each one of these guys are going to have a velocity. This would be V2, this would be V1, this would be V3. But if this whole thing is moving together like this, first things first is I know every point along here has exactly the same angular velocity, but they have different tangential velocities due to the fact that, again, the further I am away, the more velocity it has to have. But what I also know is that the tangential velocity, according to any point along here, is perpendicular to the radial vector, which means at every location along here, these are all at simply 90 degrees, which means all theta i's are simply equal to 90 degrees, which means sine of 90 here is simply equal to 1. So I could rewrite this then as the sum over I of MI/RI times VI. But again, I also know that the angular velocity is related to the tangential velocity by simply the radius. So this guy is equal to the radial distance, in this case R3, times the angular velocity of omega. So all VI's are related to omegas by simply those RI's. So this is the same thing then as the sum over I of MI/RI squared times omega. But this quantity here, based on what we talked about with rotational kinetic energy, this is simply the moment of inertia. So this is equal to then the moment of inertia times the angular velocity. So for a rigid body, something like this eraser, or this ruler, or this wheel, the angular momentum of this object, meaning how much momentum does this thing carrying while it's moving through a circle, is simply given by its moment of inertia about that particular pivot point times its angular velocity. Now, let's go back to conservation of angular momentum. So what does this say? So this says, again, as long as there are no net torques acting on the system, the angular momentum must be equal to a constant. So that just simply means that the initial angular momentum must be equal to the final angular momentum. Now, what are some examples of this that we've seen in practice? Well, one is a figure skater. So if you ever watch figure skaters skate around, what we notice is that they start doing a spin, their arms are all out, they're spinning around, and then they pull their arms in, and what happens to them? Well, they start moving faster. So let's do that here. So here, I have a rotation board down here. You can't really see it. I'm going to give myself a little bit of initial rotation. A little bit better than that. So I'm going to give myself initial rotation, and what I'm going to do is I'm going to pull my arms in. So each one of these has a little bit of mass to them, and let's watch what happens. So give myself a rotation, pull in, much faster, out, slow down, in faster, slow down, in faster. So what's happening here? Well, what's happening here is there is no torque. Well, technically, there is a little bit of friction in this area. But what we're doing is when my arms are out wide like this, as I'm holding mass, what I know is, based off of moment of inertia, the distance is now much bigger, which when I square that distance, I have a very large moment of inertia. So when I give myself that initial velocity, I have an initial angular momentum, which is fixed by the initial velocity that I give and that very large moment of inertia. But then after, when I pull my arms in, I've now decreased the size of this r, so now I made it very small. I square something which is small, which is even smaller. So what happens is I then decreases, which means omega has to get much bigger to compensate for the effect. So using conservation of angular momentum, what I have in this case is that my initial angular momentum equal to my final angular momentum is equal to the initial moment of inertia times then the final angular or initial angular velocity is then equal to the final moment of inertia times then the final angular velocity, which means that my final angular velocity is then equal to the initial moment of inertia divided by the final moment of inertia times that initial angular velocity. So this is fixed, but what I'm doing is decreasing the size of this. So as I decrease this quantity gets bigger to make this quantity bigger. So again, all that's happening is when I pull my arms in, this quantity is getting much smaller, so the angular velocity has to get much bigger to make sure that this thing stays a fixed constant. So that's one example. Another example is here. So what happens if I take this wheel and I spin it? Let me hold this out here, spin up a few times, stand at my table. I'm going to raise my arms up. Whee. Pull my arms down, up again, and then back down. So what's happening in this case? Well, in this case, also conservation of angular momentum. So initially, as I spin my wheel, this thing has an angular momentum. So let's look at this point here. So I'm going to spin it this way. Its velocity is down in this direction. R vector is the vector which points from the pivot point here outward. So when my finger's in the direction of R, curl towards F, my angular momentum is this way. So initially, I have angular momentum pointing in this direction, but along this axis, I have zero angular momentum. When I put my hands up, what happens is now I'm going to take that angular momentum which points this way, point it this way, but since I had zero angular momentum initially, I have to preserve that fact, which means that if you look at me carefully, I'm actually rotating in the opposite direction as this is rotating, so that the angular momentum of this plus my angular momentum in the opposite direction gives a total angular momentum of 0. So the reason I start to rotate around, again, is to preserve the fact that initially I had 0 angular momentum along my vertical axis. So now I need to also rotate in the opposite direction so that these two things rotating in opposite ways have 0 angular momentum finally. So this is what we call conservation of angular momentum. Now, we're going to be interested mostly in collisions, just like we were with conservation of momentum. Those collisions that we had are the same collisions that we have now. So again, we have 3 types of collisions. We have the elastic collision, which in this case means, again, angular momentum is conserved, but energy is also conserved. In this case, it's going to be rotational kinetic energy. So as an object comes down and hits, and the 2 objects come apart, in that case, it's going to be rotational kinetic energy. We're going to have inelastic, so again, if they come out, hit, and bounce away, in that case, again, angular momentum is conserved, but rotational kinetic energy is not conserved. So we have energy lost to the system. Finally, we're going to have completely or perfectly inelastic collisions. So in this case, these 2 are going to come down, hit, and then move together as one. So in that case, they're going to stick together. Again, energy is not going to be conserved. Again, rotational kinetic energy will not be conserved, but angular momentum will be conserved. So again, in those 3 collisions, we'll still have angular momentum is conserved. But again, in all 3 of those different situations, energy is only conserved in elastic collisions, but is not conserved in inelastic or completely or perfectly inelastic collisions. So, next time, we'll look at some examples of that.